Welcome to the Explainer. So if you've been glancing at consumer hardware or data center specs lately, you've probably noticed we are literally drowning in an alphabet soup of processors. We've got GPUs, NPUs, APUs, it's a lot. Today we're going to unscramble all of that and completely decipher the silicon.
Okay, let's dive right into this by asking a very fundamental question. Is the CPU still working alone? Because for decades, we kind of thought of the central processing unit as the absolute center of the computing universe, the lone genius doing all the heavy lifting. But as we'll see, modern computing has fundamentally evolved way beyond a solo act.
To get there, we'll quickly meet the orchestra. Take a look at our heavy lifter, the GPU. Check out the NPU AI engine, see their ultimate integration, watch how they play together, and finally, wrap up with how we measure success.
All right, Section 1, Meet the Orchestra, the system conductor.
The absolute best way to understand a modern computing system is to stop thinking of the CPU as a solo performer and start thinking of it more like a conductor. Workloads have gotten incredibly intense, and the CPU simply cannot do it all by itself anymore. I mean, we're asking our machines to render high-fidelity 3D graphics, run really complex machine learning algorithms, and process real-time AI. If a standard CPU tried to do all of that solo, the immense heat and latency would literally bring your system to a grinding halt. So the conductor needs an orchestra of specialized coprocessors to actually play the music.
And that brings us to Section 2, the heavy lifter, universally known as the GPU.
Now, we know a CPU relies on a handful of incredibly fast, versatile cores, but the GPU, it brings a massive parallel architecture to the table. We're talking thousands of smaller cores perfectly designed to handle multiple heavy tasks simultaneously. It's an absolute powerhouse engineered to rapidly manipulate memory. Whether that's accelerating the creation of images in a frame buffer for your monitor or crunching massive parallel math problems, the GPU brings that brute force required to get the job done fast.
Which leads us to Section 3, the AI engine, or the NPU.
If the GPU is all about massive brute force, the neural processing unit is about surgical precision. Sometimes called an AI accelerator, an NPU is completely optimized for one very specific job: the matrix math and vector calculations that underpin neural networks. Unlike GPUs, which are flexible enough to handle graphics and complex general physics, the NPU drops all of that extra baggage. By ditching those graphics rendering pipelines, the NPU skips the massive power requirements and operates as an ultra-low power microprocessor. It is just laser-focused efficiency. Now, you might be wondering how this actually affects your day-to-day. Well, as software shifts toward local AI, the NPU has basically moved out of massive data centers and right into your smartphone and laptop. It handles on-device generative AI, like running large language models completely offline. It runs computer vision tasks, think automatically framing your face on a webcam. It handles real-time audio noise cancellation, completely isolating your voice during a busy video call. And amazingly, it does all of this continuously in the background without instantly killing your laptop battery or spinning up those loud cooling fans.
Okay, moving to Section 4, the ultimate integration, the APU.
Now, what's really interesting here is what happens when we put all these pieces together. Notice how these separate components physically merge into a single silicon die. An accelerated processing unit, a term heavily popularized by AMD, is literally one physical piece of silicon. But on that single die, you've got your CPU cores, a powerful integrated GPU, and, in modern hardware, an NPU. And because they're all sitting right there on the exact same chip, they get to share a unified memory controller. To really grasp why this is such a game changer, look at the contrast in architectures. In a traditional system, you have your main CPU over here and your discrete graphics card all the way over there. Data has to travel back and forth across the motherboard's PCIe lanes. That physical distance creates latency, and pushing data across the board drains a ton of power. Plus, they have completely separate pools of memory, so they constantly have to copy data back and forth. But in a modern APU architecture, there is zero distance. The components are millimeters apart. They share the exact same pool of unified RAM simultaneously. No copying, no travel time, just hyper-efficient processing.
And this specific architecture is the exact magic that makes some of today's most exciting devices possible. Think about handheld gaming consoles like the Steam Deck or the ROG Ally. They rely entirely on custom APUs to deliver desktop-class 3D graphics in a portable, battery-powered shell. It's honestly incredible. Thin and light Ultrabooks use them to give you competitive graphics and AI without the bulky weight or, terrible battery life of a dedicated graphics card. Even budget desktop PCs use APUs to deliver highly functional performance without forcing you to buy a standalone GPU. Pulling this all together, the distinct rules become super obvious. Focusing on power consumption, you can really see the massive contrast between the GPU's high demands and the NPU's ultra-low usage. The APU essentially acts as the perfect balancing scale here, bringing them all together into a single system-on-chip form factor, perfectly balancing thermal loads and efficiency on one die.
All right, Section 5, the symphony, the division of labor.
And this brilliantly illustrates a really common misconception. A lot of people think these processors compete with one another, but in reality, they collaborate through a highly dynamic division of labor. Step 1. The CPU acts as the system conductor, running your operating system and directing data traffic. Step 2. When you fire up a heavy game or export a 4K video, the GPU seamlessly takes over the heavy parallel lifting. Step 3. All the while, the NPU is quietly running in the background, handling sustained cognitive tasks, like blurring your webcam background or managing biometric security, without you ever even noticing. It really is a perfectly orchestrated workflow.
Finally, let's wrap up with Section 6, measuring success, hardware metrics.
When you're actually out there shopping for your next device, what do the numbers on the side of the box actually mean? Well, manufacturers use distinct metrics for each processor. For the GPU, you're going to see T-flops or teraflops. This measures trillions of floating point operations per second, basically indicating raw graphical and mathematical throughput. For the NPU, the big buzzword right now is TOPS, which stands for trillions of operations per second. This measures how many trillions of AI matrix math steps can be solved under really tight power limits. And for the APU as a whole, the ultimate metric is performance per watt, measuring how much total computational power the system can deliver without overheating or killing your battery.
I want to just pause on this word for a second. Trillions. Really think about the mind-boggling scale of what is happening locally, right there in the palm of your hand or on your lap. T-flops and TOPS, literally trillions of operations happening inside consumer electronics every single second. It is an absolute triumph of modern engineering.
Which leaves us with this final thought. We've moved from the CPU working alone to this beautiful, highly efficient symphony of specialized silicon. With the GPU and NPU now sitting together on incredibly efficient APUs, the power at our fingertips is growing exponentially. So, what will trillions of local AI operations unlock for you next? I hope this explainer has given you the structural foundation to understand exactly what your hardware is doing behind the scenes. Keep learning, keep exploring, and I'll catch you in the next explainer.